So I guess today we're going to do the last lecture on reinforcement learning, and I'll probably spend like 5 minutes to briefly wrap up the whole course, but mostly we're going to talk about reinforcement learning. So, this is supposed to be a more kind of like an introductory lecture on some of the a little bit more advanced topics in reinforcement learning. So I wouldn't talk about a lot about details, but mostly I'm going to define some terms, and so that it's easier for you to kind of like either take another course on reinforcement learning or read some of the literatures yourself. So I guess last time we have introduced the basic concept of MDP, a Markov decision process. That's the main language that people use to think about reinforcement questions. I'm going to start by just reviewing some of the key idea. So recall that you have an MDP, Markov decision process. This is kind of like it's described by a few important concepts. So one thing is the state space. You have to specify the state space to specify the MDP. You have to specify the action space. And the MDP has this transition probability, which is called PSA, for every S and every A. S is in the S is the state, A is the action. For every S and A, you have this so-called transition probability matrix, transition probabilities, which is to describe what is the probability that if you start with state S and take action A, what is the probability to arrive at a new state? So, and there is this so-called discount factor gamma and a reward function R. So after specifying these 5 quantities, you get the MDP. And we also talk about the concept of a policy. So policy is something you are trying to learn from interacting with the system, the environment. You are trying to learn the so-called policy, which is a function that maps from the state and action. So this policy tells you what you do, which action do you take when you see a state S. So pi of S is the action you take when you are at the state S. And we also introduced these two type of value function. So the first type of value function is the value function of the state S. So this is the value of the state S under the policy pi. So this is the expected reward, expected future payoff, of executing the policy pi from state S, right? So you keep taking action from the policy pi. You start with state S, and then you compute what is the total future payoff in expectation, and that's V pi of S. So, and we also discussed this so-called V star of S. This is oblivious to the policy pi. This is asking, what's the maximum possible reward you can get from starting from state S, right? So you maximize over all possible policies, and you look at you maximize the V pi of S. And the maximizer of this process, the argmax of this, is kind of the optimal policy you care about. You want to find out what is the optimal policy. All right, so I think we probably didn't have time to define this, formally last time. So the optimal policy pi star is the so-called the argmax pi, V pi S. And this is actually there's a unique pi star that maximizes the V pi S for every S. Just because the policy itself is already a function of S, right? So you are finding a policy that maps the function S to the action A. You already can take different actions for different state S. So, and this is one way to define this, and another way to define this is the following. So this is another way to define the optimal policies. You say that this is the greedy policy with respect to V star. So this is an alternative definition of the optimal policy, which is defined to be pi star of S is defined to be the best action you take such that you maximize your future payoff. What's your future payoff? The future payoff is equals to R of S plus the payoff you get from the future steps, which is gamma times this PSA S prime. This is sum over S prime. This is the probability that you see S prime after you take action A, which is the variable here, and then you times V star S prime. Right, so this part is the expected reward you take. The best reward you can get after you take after you take action A. Right, you take action A, you have some chance to arrive at S prime, and you multiply the best payoff you can get after starting from S prime, and so that's why this is the best possible expected payoff after you take action A, and this is the payoff you get at state S. So the total thing is the best payoff, including the current payoff, the current return, the best future payoff if you take action A, and you maximize over A, and that's the best policy. That's the definition of the optimal policy, right? So because this is already the optimal choice, you're already thinking about the optimal choice for all the future steps, and then you take the action A that is the optimal for this step, taking into account the future steps, and that's the optimal policy for the state S. Any questions? And in some sense, this is the way to find out the optimal policy, because if you find out what's the V star, then you can find out the optimal policy, because you just take the greedy policy with respect to V star. And we also introduced this important concept of Bellman equation, which is the main tool that we use to compute V pi and V star. So for V pi, if you're given pi, then the Bellman equation for V pi, is this. So V pi of S is equal to Rs plus gamma times this. Right, so most of the Bellman equations you can pretty much verify intuitively yourself, right? So because what is the reward, the payoff when you are at state S, executing policy pi? You first look at what's the current reward for this step, and then you look at what's the future reward. The future reward can be computed by considering all different possible outcomes of executing pi of S, right? So if you apply pi of S, then you have some probability to arrive at S prime, and you multiply that probability with the payoff you get after arriving at state S prime. Okay, and this is and one of the important things here was that this is actually linear in the variable V pi S. So linear in this in the variable V pi 1 up to V pi m. I think I used m as the number of total states. So this is a linear equation of these variables. So you can solve the linear equation by any linear system solver. And we also introduced this Bellman equation for V star, which is of a familiar form, but the difference is that now you don't have the pi, you have to maximize the action. So you have Rs plus the max. You take the the best possible action that maximizes the future reward. Right. So now this is not a linear system of equations in terms of V star, but you can use the so-called the algorithm we introduced last time was this iterative algorithm that you do the Bellman update iteratively. You can do this iterative algorithm to find out the V star. Any questions so far? This is basically a review of the last lecture. So, okay. So far we have dealt with, in the last lecture we have dealt with known dynamics, right? So in all of this, right, so we have described the algorithm and so on and so forth. Everything was, was kind of like under the assumption that the algorithm, so basically the algorithm to solve the V pi or the algorithm to solve V star, the iterative algorithm. I guess I'm not sure whether you still remember the algorithm. The algorithm here was just something very simple. So you take a loop and you just say, I'm going to update V. I have a working memory for V. I update V like Vs updated to be something like Rs plus max. Okay. Right, you just compute the right-hand side, and then with the V plugging in here, and then you update the left-hand side with itself. So this is called value iteration. The algorithm is called value iteration. So both the value iteration algorithm and the algorithm that solves the linear system equation in this case, both of these two algorithms are assuming you have a known dynamics. So the PSA is known, or the family of PSA is known, in both of these two algorithms, because you have to compute PSA, right? So in the RL language, you are saying that this means that you have the known transition dynamics or the known environment. That's how people refer to these kind of settings. So, but in reality, what happens is that this PSA is not known anymore. So, for example, thinking, sometimes you do know it, right? For example, suppose you consider this is a game like playing Go, right? You are playing the Go or chess, so you do know the rules of the game, right? You know what happens if you play an action A, what will happen next, right? So you're going to move this, each of the piece, in some way, right? So you know the rules, then in those cases, PSA is known. But in many other cases, the transition dynamics is not known, right? So for example, when you control the robot, right? So in some cases, you probably know a little bit about, if you control this, the robot would move forward. But sometimes if you're doing the low-level control, you are changing the joint of the robotic arm or the hand, robotic hand. You don't exactly know how everything moves exactly. You probably have some rough sense, but you are never able to model them exactly. Actually, this is a challenge. So this is actually the reason why kind of like now people are using more and more learning techniques. So I think in the early days, I think, for example, there was a company called Boston Dynamics. So what they do is that they basically just use rule-based. So basically, they build this PSA. They try to figure out from physics what exactly this dynamical system should look like, and then they build their policies based on that dynamical system. So, but these days, I think people are kind of like at least trying to apply more learning techniques, because there is no way you can figure out exactly what PSA is just from the physical rules. You have to use some kind of like learning-based technique. Sometimes also it involves interaction with environments. For example, suppose I have a robot that is moving on this carpet, then the speed would be different from the robot moving on the hardwood floor, right? So the other environments also part. So like the floor, the other things also part of the environment. So then you can never model everything perfectly, right? You would never know the texture of the floor exactly. So that's why we have to learn the dynamics to some extent. So I think that's in some sense that's the real problem in reinforcement learning, where the dynamics is unknown. So when you don't have the dynamics, right? So what can you do? So you have to know something, right? You have to somehow have some information about dynamics. So the typical assumption, which is that so the PSA, this is unknown, but you have given a state S and an action A, we can sample S prime from this transition dynamics. Basically, you can just try the robot in the real world. We can just say, I'm going to try my action A in the real world and see what the next S prime is. Right? The S prime will involve a lot of stochasticity, there's some randomness, but you're going to observe one random sample from this transition dynamics. So that's why when people call sample complexity, it means that how many times you have to try this, right? For how many state and action you have to try to see S prime by just try it in the real world. So that's how people generally learn. So you learn by interacting with the environment, by trying all these actions, and you somehow learn the dynamics in some way. So that's the basic assumption. And then there are two types of algorithms in reinforcement learning that are the most popular. I think most of the algorithm can be either categorized into one of this group. So one type of algorithm is called model-based RL. So here the model means the dynamical. The model means the dynamical model or the transition dynamics. So as the name somewhat suggests, basically model-based RL means that you explicitly learn the transition dynamics. How do you learn it? That there are multiple variants. It depends on the situations, depends on how complex your dynamic is. But the transition dynamics or the transition probabilities. I guess they mean exactly the same thing for they probably just always mean exactly the same thing. But sometimes people have different terms. So basically you learn this PSA explicitly. You build a model to describe this PSA. And you learn this model from the samples. The samples are the data you learn from. And then you build some approximate PSA from the samples, and that's typical kind of like types of the typical types of kind of like model-based RL algorithm. So from samples. Okay, so and there is another type of algorithm which is called model-free RL. I don't think there is really a precise definition of any of this, but in some sense, the model-free RL, I would just say, is a negation of this, right? So you don't explicitly learn a transition probability. So just the doesn't learn the transition. So it sounds a little bit kind of like if you don't have any context, this sounds might be a little bit tricky because how come you don't learn the dynamics but still learn the policy? So it's possible. For example, sometimes you can just directly optimize this without learning the dynamics, right? So you can probably just you use some kind of like a stochastic. So there are ways to not learn explicit dynamics. Of course, eventually any algorithm needs to somehow have some understanding about dynamics internally in some sense, but you don't have to explicitly build one. Right. So for example, one possible option is just that you optimize this function v pi i's over the policy pi. Suppose you can somehow take gradient descent over policy pi, then you can avoid dealing with the dynamics, right? You don't use the Bellman equation. You just somehow compute the derivative of this with respect to pi. So some of the buzzwords, are like some of the algorithms. Q-learning is one type of algorithm. And another type of algorithm is called policy gradient. So I don't think we have time to discuss any of this model-free algorithm. I just want to write them down here, just the buzzwords, so that if you happen to kind of like came across them, then they are model-free algorithm. So in some of the quarters we do cover this. Some of the quarters have one or two more lectures, like depending on how many holidays there are. Okay, so and another kind of like some of the kind of the definition of terms people use here is that there is something called, when you say tabular case or the tabular RL, this means that you have discrete state space, discrete action and state space. So in other words, the size of the state space is finite, and the size of the action space is also finite. And actually implicitly you are, in some sense, whether it's finite or not probably is not the most important thing. The real important thing is that the state and the action space are not too big. They are not like a billion or something. They are something that, that is reasonable. Like in the last lecture, we are basically assuming this, right? We assume that the state space is like has m entries, right? And we didn't talk that much about action space, but we implicitly say that we actually all the algorithm require that the action space to be somewhat kind of finite. And you can see like this, for example, this linear system solver algorithm. If you want to solve the linear system equations, what are the variables? The variables are the v pi 1 up to v pi m, where m is the number of states. So if m is infinite, then you cannot solve this linear system equations, where you have infinite number of variables. Even if m is not infinite, even if m is something like super big, say like exponentially big or something like a billion, then you cannot really afford time to solve this system equations. So in some sense, the most important thing is that you really don't want to have, like if you are a tabular case, you are implicitly assuming that the state space is not huge. But as you can see, sometimes the state spaces just have to be infinite or very big because you have the state space is continuous, right? So that's another case where you have continuous state space. Sometimes you have continuous action space as well. So for example, the state space is something like RD. So you have a d-dimensional vector to describe the state, and your action. Typically, the action space is smaller than the state space. Maybe the action space is something like RK, where K is smaller than D. Sometimes D can be like 100, or maybe sometimes even more than 100. Action space typically, if it's continuous, then K probably would be 5, 10, something like that. And sometimes you have the combination, right? So you have continuous state space, but finite action space. That's also possible. For example, one typical case where you have continuous state space, but a finite action space is Atari game, right? You play this Atari game, and your state space is this pixel space where you see the pixels, right? So that is shown to you, and the actions, but are actually finite. You just have a few buttons and maybe some kind of like handle you can choose to play. So the action space is somewhat finite. All right, so these are just some kind of like terms, just in case they are useful when you read some of the other books or literatures. Okay, so then in the next 20 minutes, I'm going to discuss, how do you do the model? Maybe in the next 30 minutes, how do you do the model-based RL for the tabular case, right? So basically, you can see that they're model-based, model-free, and tabular continuous, right? It's kind of like you have like 4 combinations, and we're going to do the model-based plus tabular. So, and this is actually not very hard. So what you really want to do here is that basically model-based, tabular. You want to learn an explicit model that kind of like somewhat similar to the true model PSA. So what you have is that you have a collection. So suppose we have a collection of trajectories. I forgot whether I defined trajectories. By trajectories, I just mean a sequence of like state actions. So suppose you say you have some state S0. Maybe let's say you start from the state S0, and you take some action, maybe A0, and you arrive at S1, and you take some action A2, A1, and you arrive at S2, so on and so forth. Right? So this is the one trajectory, right? A sequence of state actions, right? So so far I didn't really tell you how I got this trajectory, but I'm going to talk about how do you learn the transition probability from some given trajectories. Right, so suppose I give one trajectory, and often you need more than one trajectory. So then you say, after I take a bunch of steps, maybe I take T steps, I reset. So I reset, and then I get another trajectory. Let's call it maybe let's call this trajectory S01, A01. I have the superscript just to indicate that this is the first trajectory. And then I reset, I get a new initial state, and I call this S02, and I apply A02, S1 to A12, so on and so forth. So I get and maybe I can get more, right? I get a bunch of trajectories. Here the subscript is indexing the time, and the superscript is indexing which trajectory you are in. And then how do you estimate the transition dynamics? Recall that all of these state and actions are discrete variables because I'm in a tabular case. So basically I just have to estimate PSA S prime, right? What's the chance to start with S and take action A and arrive at S prime? So this is kind of like in some sense the problem is the same as some of this, like I think we discussed this generative learning algorithm where we have this event model, right, where everything is kind of counting based. So basically you can compute the maximum likelihood of this transition. You view this as a parameter, right? So this is something you want to learn, right? This is a parameter, and then you try to find out the maximum likelihood estimate for this parameter. And it turns out that it's just as usual, it's the most kind of natural choice. Basically, you just count on the frequency to see this, right? You say in the denominator you say I look at how many times let's say we took action A at state S. So you basically look at all the cases where you take action A and state S. And then in the numerator, you count how many times we took action A at, okay, I guess maybe I'm a little too wordy here. So basically, the number of times if you take action A and state S and you arrive at S prime. So the denominator is the total number of times you take the action A at state S. And the numerator is how many, among all of these occurrences of S and A, how many times you indeed arrive at S prime. And then that's your transition probability. That's your estimated transition probability. This is an estimate for PSA. Right. So, any questions so far? And once you have this, it's just a counting-based algorithm. You just count how many fractions you really arrive at S prime. Among all the SA, how many fraction of those really arrive at S prime? And that's the empirical frequency is your estimate for the transition probability. Wait, I'm using the right, maybe I should use the black color. Okay, so, and once you have this tool to estimate the transition probability, then you can have a model-based RL algorithm. I'll still use the red if it's okay. I think the black one doesn't seem to be very good. So the model-based RL algorithm is doing the following. So it's pretty intuitive. So first of all, you initialize some policy pi, maybe randomly, let's say. And then you have some data set. Initially, you have no data, so the data set D is empty. I'm just defining a notation, basically. I'm going to use this data set D some way. So, and once you have this, and then what you really do is that you say, I have two steps. The first step is that I'm going to estimate, I'm going to collect some data. So collect data by executing policy pi. So if you execute policy pi in a real environment, you're going to get some samples, right? That's our assumption. Our assumption is that you are able to get samples from the real environment. You don't know the PSA, but you can get samples from the PSA. So you actually your policy pi to get your environment. So basically, what you do is you get a family of environment. Sorry, you actually your policy pi to get some samples. And the samples you got, let's say they are denoted by S01, something like, and you apply A01, and then you get S11, so on and so forth. And you have S1, S02, right? This is the same kind of set of samples here. So you get some samples. And then you add all of these trajectories, add the trajectories to D. So D is a kind of like a set of data. And then I guess I'm using the board space in an awkward way. How do I think I'll just I have to. So let's say I'm going to. So you get this data, this kind of data, right? So this is a set of data that is kind of like this. Okay. So and then you add them to D. Okay. So in the second step, this is the first step. You collect some data, and then in the second step, you estimate the PSA using data in D. Okay, so and let's still use PSA as the estimator, right? So suppose you get some PSA that is supposed to be an estimate for the real transition dynamics. And then in the step C, so you can use, for example, use value iteration. Or it could be also policy iteration. I guess we didn't have time to discuss policy iteration in the last lecture, but if you are interested, you can read lecture notes to see what's the policy iteration. But let's say suppose you use value iteration to get V star, the value function for the estimated PSA. The estimated, dynamics. So you just pretend that the estimated dynamics is the real dynamics, and then you solve the best policy, the optimal value function for that dynamics, and then you take pi star you take pi be the optimal policy for the estimated dynamics. Okay, so are we done? So it sounds like we're done, right? Because we estimate some. It's kind of everything is simple, right? You collect some data, you estimate the dynamics, and then you get the best policy on the estimate dynamics. But actually, what you really have to do is you have to have another loop, outer loop that repeat this process. So what you really need to do is you have to take a loop, and so that after you have some policy pi, you want to collect some more data using the current policy pi. Initially, the policy pi was random, and you collect data from the random policy. And after you get some policy pi, then you should take another loop to collect more data, and then re-estimate your transition dynamics, and then recompute your policy, and then you keep doing this. You probably don't have to do a lot of loops, but you have to do some iterations. So the question is why you need this loop, outer loop, right? So why we cannot just go with the first dynamics, right? We have estimated, right? So if you estimate one dynamics, if it's accurate enough, then why we cannot go with that? The reason is that in RL there's this problem with this kind of like so-called exploitation trade-off, which I'm going to elaborate. So the immediate problem is the following. So it's possible that in the first round, when you collect data, your data is not very good. It's very bad, low quality data, right? So for example, suppose you want to control a robot, and you initialize your policy randomly. You just do some random, you just push the random buttons or control the robot in a random way. Then the data you collect are basically just some kind of like the robot is just kind of like wiggling around a little bit, right? It doesn't really move much. So the data you collect is actually very, very bad. And then even you have a lot of data, you still your data quality is not good enough just because the robot doesn't really do much. And then your estimate dynamics is also not going to be good enough. And then your policy is also not going to be good enough. So what you really want is that you want to do this iteratively so that next round, when your policy is kind of like reasonably okay, you collect some higher quality data. And then you do this again, and then your policy becomes even better, and then you get even better, higher quality data. So that's why you want to have this loop. Another example, is the following. So suppose you have, this is another example. Suppose, for example, let's say, I guess you probably some of you have used this kind of like a automatic robot to do the cleaning for the house, where you have this small like vacuum that can, like a robotic vacuum that can move in your house, right? So if you have used that, I think how it works is that it first kind of like explore your whole room and to try to figure out what your room look like, and then the next round is gonna kind of like do some kind of like take some trajectories to kind of clean your room, so that it covers every part, right? So something like that. However, but if you think about this, right? Suppose you have, say, for example, say something like you have a big room, and then you have a small room adjacent to it, right? So you have some robot that kind of tries to clean the room and navigate through the room, right? So what if in the beginning your robot only kind of goes to this part, right? So it just, in the first round, your policy just only look at this room. Then your dynamic model will only be able to is only accurate for this room, right? You only know what's happening in this room. What's the chairs? What's the stairs or other kind of like sofa, so on and so forth, right? So but you don't know anything about this one. So that's why you cannot. So that's a typical situation where the data of the quality of the data is not good enough, because the quality of the data, it doesn't even cover some part of the room. So then if you don't do anything special, then your robot wouldn't have incentive to go to this room, because the robot doesn't even know the existence of this room in some sense. So this is actually even more challenging case, because here, even if you just do this loop, you wouldn't be able to kind of like figure out this small room, because at the beginning you just only see the large room, and you never look at the small room, and then you figure out the optimal policy to clean the large room, and you still don't know the existence of the small room, and you just keep doing this. Eventually you just only kind of clean the large room, and you just never know the existence of the small room. So in these kind of cases, you need even something more than this kind of algorithm to be able to work. So and typically this is called this is a phenomenon called exploitation versus exploration. So exploitation basically means that you believe your current transition dynamics. You just strongly believe your current transition dynamics, or your current kind of understanding about the world, the environment, right? And you just try to find an optimal policy for that, for the current understanding about the world. And exploration means that you try to explore different kind of strategies to see whether you miss anything in this world, right? So in this case, maybe you missed the small room, so you want to do exploration to figure out the existence of the small room. And exploitation really just means that you just basically do the best thing for the current map. So as you can see, you need some exploration to kind of at least cover the entire kind of like the entire world so that you know like the existence of any other options. So typically, if you really run this kind of reinforcement learning algorithm, you have to add some randomness in the policy pi, so that you can have some exploration, right? So you don't want to just always in every round you just always collect data from the policy pi that is optimal for the current environment. You also want to have some exploration by adding some randomness. So basically, what you really do is that when you collect data, you add some by adding pi with some randomness. So in this case, you have some small chance to go into the small room so that you can see the small room, and then you figure out you should actually kind of clean that small room, with some kind of like a trajectory, with some actions. So maybe another example is that, for example, suppose you can figure out which restaurant you want to go, right? In Palo Alto downtown, right? So suppose you just so far you know 2 restaurants, and you know one of them is better than the other for you. And the exploitation would mean that you just always go to the better restaurant for your taste, right? And then you just keep go to that better restaurant for you. However, you may also consider some exploration because there are many other restaurants in Palo Alto, and you don't know the existence of them even, or you don't know whether they are good or bad. You don't know their taste, whether their taste fit you. So exploration means that you should try some of the other restaurants, even at a risk that those restaurants are not as good as the one you have known, but you want to try more try to kind of explore those restaurants. And exploitation means that you just believe that, okay, there's nothing I should explore anymore. I believe in my current evaluation of all the restaurants. I just take the best one, and I keep going to that that one. So and there's a trade-off, because if you keep doing exploration, then you keep trying all different restaurants, then inevitably you are going to find some restaurants that are not very good, right? So and you're going to suffer. You're going to say, okay, this doesn't worth the money. You're going to have some bad dinners in some sense. But on the other hand, if you're only doing exploitation, you're going to miss other opportunities. So it really depends on. And if you really go into the RO literature, there are different ways to trade off these two things, right? Depending on how confident you are with each of the choices, you may decide to exploit more, or you may decide to explore more. Okay, but I think we are not going to have enough time to go into the details. There's a huge literature here. Like even just when you're talking about this going to restaurant thing, right, which doesn't have a sequential aspect. You just go to the restaurant and have lunch or dinner. There's no sequential decision. You still have to think about the exploitation and the exploration trade-off. So it's a kind of like to do it optimally, you have to be somewhat kind of careful. Okay, any questions so far?
So my question is, when we are doing the exploration, so do we know that we are gaining better understanding about the world we are in, or we are just trying by random?
Yeah. So I guess maybe you're asking about how do we do exploration, right? So what's the kind of the guiding principle for doing exploration? And it seems to suggest that one principle could be that you only want to explore when you can collect more information. Yes, I think that's basically it's pretty much like what you said. But sometimes random actually can serve that need. So if you just do random perturbation of your current option, typically you get a actual good amount of information. But of course, in some other cases, you have to directly go for those kind of uncertain places. Actually, you are exactly right. So for the tabular RL case, typically what people do is not just random exploration. What people do is you say you take those actions that are most uncertain for you. So suppose you have some action that you don't know what the outcome would be. You have no idea what the outcome would be, or you have very little idea. You have very huge uncertainty about what the outcome would be. You try those actions more as exploration strategy. But for the continuous state space, right? So I think it turns out that most of the algorithm works are kind of like a local randomized exploration. You don't try some crazy option. You try in your neighborhood. I think that actually probably make a lot of sense in those cases where you have so many different actions, right? So for example, if you think about your career planning, if you really have, suppose you in theory you have really a lot of actions, actions you can try. You can, instead of being at Stanford, you can try to be a professional soccer player, right? So or you can be a musician, you can be many different, there could be many things. And then you are very uncertain about some of those probably, right? So like I wouldn't know what if I try to be a musician, what would happen. So but I think when you have so many actions, typically, I wouldn't say this is not 100% true, like in the algorithm, when you talk about technical details, but typically when you have so many actions, I think somehow the algorithms, most of the working algorithms tries to explore locally. So for example, I'm a student here at Stanford, and then I try something somewhat similar, maybe going to intern at Google, or maybe maybe trying graduate school or something like that. But I wouldn't try something completely kind of different. We don't have like a strong theory to say exactly what you should do. So these are just it's a mixture of like some theoretical explanation and some kind of like empirical observations. Okay, so I guess so I'm going to use the rest of the 40 minutes or 35 minutes to talk about continuous state space. So I have talked about model-based RL, right? So now I'm going to talk about model-based plus continuous state space. And the idea is pretty much similar. It's just that you have to somehow you have to deal with the continuous state space. You will see there's some challenge. So by the way, this reinforcement is kind of interesting area. Like at least when I kind of like after I learned it, I feel like it has a lot of things to do with your kind of like life decision as well. Like of course you cannot only 100% trust the algorithm. Like it's not like you should implement the algorithm in your life decisions. But there is some kind of like insights there that is useful for the general kind of like this, this is you can model your life as a reinforcement algorithms. It's just that, okay, one difference is that in the real life you have much more information. Like in the theoretical formulation, you are only collecting information from the samples, right? So you know nothing about the environment at the beginning, and anything you have to try it out, right? Like if you want to know anything about PSA, you have to try it out, and sometimes you can try more, and sometimes you can try a bit less, but you still have to try. In life decisions, in many cases, you don't have to try. You can already predict to some extent what the outcome is. Other than that, I feel it's pretty similar. Just my 2 cents. Anyway, so I guess so. What do you do with continuous state space? Continuous. So one easy case, just to start with, is when D is 2. Suppose you have the state space is only dimension 2. I think in this case, basically your state space is a 2-dimensional plane. You have like maybe like two axes, and one way to do it is that you just discretize your state space into discrete variables, right? So before each of the state is like 2 real number, but then you say I'm going to discretize the state space. There's some boundary, of course, because the state cannot be too big, and then you discretize something like this. And then for every cell, you say all the states. There are infinite number of states in each of the cell, but you say all the states in that cell is going to be treated as one state, just because they are all pretty much similar. So as long as you have like fine enough granularity here, then you can basically treat every cell as a single state. So, and suppose you have like granularity epsilon, then you are going to have 1 over epsilon squared. 1 over epsilon choices for the first one, 1 over epsilon choices for the second one, so you have 1 over epsilon squared choices of states. And you can probably take epsilon to be something like 0.01, I don't know exactly, but you're going to get arrive at a reasonable number of states. Maybe quite a lot, but not like maybe 1,000 or something like 10,000, but it wouldn't be too bad. So that's easy choice. However, this doesn't really work for when your dimension is higher than 2. I think when your dimension is 3, it already becomes tricky, because if you think about, you are discrediting the 3-dimensional space, then say suppose D is 3, and you do this 1 over epsilon kind of like, each of this size of each of this cell is epsilon, then you need 1 over epsilon to the power 3 states. I guess it depends on what epsilon you choose, but if you choose epsilon to be something like 0.01, then you have like 100 to the power 3, that's like a million, which is already a lot, right? So maybe sometimes it's still okay, but generally when D is 3, it's already kind of tricky. And then you can see this doesn't scale very well, because if you have D is, for any D, this would be 1 over epsilon to the power D, and when D is 5, basically it's kind of impossible, completely impossible. So we need another approach for, but actually, just to clarify, so when D is 2, actually this is actually typically a pretty good idea, because it's simple and clean, and when you don't have to deal with any other complications. The only thing is that you have 1 over epsilon square states, but there's no any other complications. It's actually a pretty good solution. I think it probably should work in most of the cases. So, but when D is more than 3, it's going to be a problem. So basically what we do is we're gonna redesign everything that we have discussed, with continuous state space in mind. So I guess there are 2 questions. One question is that how to learn PSA for continuous state space, and then question 2 is that how do you do the value iteration both for continuous state space. So for question 1, so let's discuss each of them. So and the basic idea is that you try to kind of like extend what you have done to the continuous state space in some way. So regarding question 1, so how do you do it? The first question probably is that how do you even represent the PSA, right? So now you have infinite number of S here. So before, for every S and A, you have a vector to represent, right? And so for every SA, this PSA is a distribution, and it's a vector over m possible choices if m is the number of states. But now you have infinite number of S here, or maybe exponential number of S there. And for every PSA, this vector is actually a very high dimensional vector, maybe a exponential dimensional vector or infinite dimensional vector. So how do you even represent this? So the idea is that you can change the way to represent it. You don't represent this. You can do the following. There are many ways, but this is one way that is probably common. Learning dynamics. So what you do is you first say, I'm going to model this process S prime is sampled from PSA by assuming S prime is equals to FSA plus some noise. This is one option, not the only option, but the one option is you assume that S prime is computed by applying some function on S and A, and then add some noise. That's my way to sample S prime from this distribution. So this is a way to define a distribution. The distribution basically has mean FSA and some Gaussian has some variance, like a Kasai, like the same as the Kasai. So this will give you a random variable S prime given S and A. So and this FSA, let's say maybe FSA is deterministic. This is just some function you want to learn. And this part is the noise that gives you the stochasticity. Maybe let's say Kasai is maybe from some 0 with some covariance sigma. So sometimes you just I guess probably I've seen that this is kind of almost the same as what we do with supervised learning. You just treat this as a supervised learning problem. So S prime is my label, S and A are my inputs. So I'm just trying to predict my label from the inputs. And the way I model this is I model this by some kind of like some function plus noise. Right? And then you can do maximum likelihood. And the maximum likelihood is just the square loss. So, and you learn that you learn this model F by some square loss. So for example, so you have to introduce some parameterization for F. So for example, F could be a linear model. Suppose you say you have some parameter A and B, and your F could be just A S plus B little a. Right, so this could be your F, which is parameterized by A and B. So A and B are parameters, S and A are inputs. So you just have this linear model. I think this is called linear dynamical model. So this is a linear model. And another option is that you say, I'm going to say FSA is equals to maybe you can use the same idea as the feature, when you do the kernel, you can say this is like something like A times phi of S plus B times, I don't know, I forgot what this is called. Like this is called. You just have some other feature, something like this. So both of these two phis, these are some features. Right. So this is like what we did with kernel method, right? So you introduce some features and then you are linear in the feature space. Of course, you can also say that FSA, so I guess here the parameters A and B as well. You can also say my FSA, if you are parameterized by some theta, is a neural network applied on S and A, something like this. And this neural network is maybe, say, parameterized by theta. So you just say S and A are concatenated as inputs of a network, and you apply this network with parameter theta, and the output will be my FSA. And in each of these cases, you can model your S prime like this, and then you can try to find out the, and this becomes a supervised learning problem. So what I mean is that once you have the parameterization, right, so then you can say the learning loss function is that, say, suppose you have some data. Suppose data are something like, I guess I've written this several times, S01, A01, S11, so on and so forth. So you have a bunch of trajectories. Sorry, I messed with indexing. So you have these trajectories, and then you break these trajectories into 3 tuples. So you mean that you view this them as a collection of 3 tuples, right? So you say you have S01, A01, comma S11. So this is the first 3 things here. And you view this as the input, and this as the so-called label or output. And then you say, I'm going to have these 3 things, which is S11, A11 and S12. Right, so this again is the input, and this is a label. And you do this for every 3 tuples, in every trajectory. So you get basically get a sequence of like 3 tuples. So eventually you get, as say t minus 1, n is the number of trajectories, a t minus 1 n. I guess there are a lot of indexing here, but basically just view every 3 consecutive kind of like numbers as a tuple, and you view the first S and A as the input, and the outcome as the output, something like this. Okay, so you have a data set of this, right? So this is a data set of size n times t. N is the number of trajectories, t is the length of the trajectory. And then you do a supervised learning. So you have you just use supervised learning. So you do some kind of regression, let's say. You say I'm going to minimize over my parameter, maybe let's call it theta, and I minimize this I minimize the loss over all data points. So what is the loss? The loss, so there is a I, there is also a t. I is indexing the trajectories, and t is indexing the time step. And every time you want to predict what? You want to predict st plus 1 in the ith trajectory using this function f theta s t I a t I. Right, so this is the input of this supervised learning problem. You apply the model, and then you try to match it with the output, a label of this problem. And here I'm using an L2 norm because the label is a vector, right? So in many of the cases you see this parenthesis square, because in those cases when you do the typical supervised learning problem, your label is a real number, right? House price prediction, right? So the label is the house price, which is a real number. But here the label is a vector. It's the same. You just do the L2 norm square. Sometimes you can change the loss function. You don't have to always use L2 norm square. Maybe you don't even need square sometimes. Or you can use other loss, L1, something like that. So, and once you do this, you get a theta. And this f theta will be your model. Any questions? So I think the benefit here is that before you have to specify PSA for every S and A, right, as a vector, right? So now you learn this function f theta. So the number of parameters is theta, and then for every S and A you can compute FSA, if you know the theta. So that's how you do the model-based RL part. That's how you do the model estimation part, how you estimate the dynamics. And then you also need to deal with the value iteration. How do you do the value iteration for continuous state space? I don't think I have the math there. So when you do the value iteration, before you are trying to kind of like update the value function for every state, right, every time. Right, so that's not possible anymore because you have so many states, you cannot update the value function for every state. Actually, it's not even clear how do you even describe a value function, because before the way you describe a value function is you say for every v star s, for every v star s I have a number, right? So, but before you describe it by listing all the s, right? For every s you have a number. That's how you describe v star. But now you cannot really describe it like that. So what you do is you say I'm going to parameterize the value function by, again, kind of like before, by some kind of like a neural network or linear model, right? So you can say, I parameterize, I write my VS as like something like maybe one choice is that you can say this is theta transpose times some feature of S. So this is a feature, and this is the parameter. That's one option. And another option is that you say my V of S is a neural network with parameter theta applied on a state S. Right, so then theta is a description of the value function. And you need to learn theta. Of course, there are other ways to do this. For example, one way to do it is that you can, for example, design some the right features using physical intuitions. Sometimes you know that some coordinates, it's only meaningful when it combines with other coordinates in some meaningful way. So I think some mixture of this could also work, because you could design some features and then use these features as input to the neural network. But generally, you just want to have a parameterized form. Okay, so we have done, so after we have the representation of the value function, then the next question is how do you do the update, right? So before, what we did was that, so recall the update was something like V as is updated to be something like RS plus gamma max A prime. Right, that's what we did. Right, so we have some working value for V, and we compute the right-hand side of the Bellman equation, and we update the V with the right-hand side, and then we repeat. So, but you cannot do this because you don't have, before we do it for every S. But that's not possible anymore. So what we do is we try to make this is true for the S we have seen. So basically for continuous state space, so for the continuous case, we just try to ensure the Bellman equation for states that we have seen. You don't ensure this for every state S anymore. You just ensure it for the states you have seen. And if you just want to do that, then you can do some kind of loss function to ensure that. So let me elaborate on what do I mean here. So the first step is the following. So you estimate the right-hand side of the Bellman equation for states, say S1 up to Sn. So I haven't told you exactly how I got these states, right? So suppose I got some states that I have seen, right, in the algorithm, and I want to only ensure this Bellman equation, ensure this to be equal to this, or somewhat kind of encourage that they are the same, only for this kind of choice of states, S is equal to one of this. That's my compromise, because I cannot do it for every state. So what I do is that I try to first compute the right-hand side. So how do I get the right-hand side for every state S? So what I do is I just so basically I want to compute RSI plus this max thing, right? But the problem is that here I have a sum over S prime again. That's again a lot of different choices of S. So what I do is I'm going to first turn this into an expectation. You write this as expectation of V S prime, and S prime is sampled from PSI A. So after you have the expectation, you can use an empirical sample to estimate this quantity. So basically what you do is you say, so for every, By the way, I think I forgot to mention one thing, which is that now I'm talking about continuous state space, but finite action space. Just this is a slightly simpler question than both of them are continuous, just because I don't want to overcomplicate too much. So it's continuous state space and finite action space. So what I do is I first estimate this by sampling some s prime, and then I take the max, because you have finite number of states, actions, you can just take the max. So what you do is you say, for every a, you get k samples. Let's call it S1 prime up to Sk prime. These are sampled from this transition dynamics PSA. PS SIA. Right, so on the state SI, you try the action A and you see what is the outcome. You have a bunch of random outcome. And then you define QA to be RSI plus 1 over K times this average, right? You use the empirical average, basically. Right, the empirical average of PV Sj prime. So this is supposed to estimate RS. I think I'm missing a gamma here. Sorry. It's supposed to estimate RS plus RSI plus gamma expectation VSI. Right. So I'm supposed to use this to estimate this without a max. And then I take the max. I call Y I to be the max of this QA. So then this is supposed to estimate this one. So Yi is supposed to estimate this quantity. And for every I have an estimate. Right, so for every I have estimate for the right-hand side of this Bellman equation. And then I ensure that this Bellman equation to be somewhat correct for all the i's that I have considered. So step B, I need to enforce like VSI to be close to YI. Right? Because recall that we have spent so much effort to compute this YI. It's YI is supposed to be the right hand side of the Bellman equation evaluated at SI. And I want this to be close to the left-hand side. And how do I do that? I do that by I'm computing theta to be argmax of this loss function that encourages this. And the loss function is simply just some L2 loss. Say I take the average over all the possible SIs, and I say my VSI is parametrized by some, say, neural network like this, right? So let's only talk about neural networks, but it works for anything, right? So say this is a neural network, neural net with theta applied on SI minus YI square. So basically you want this neural network to output the right value function that matches the target. The target is the right-hand side of the Bellman equation. Actually, in the RO papers, you do call this target. So this is the target you want to kind of match, and you want to choose the theta, update the theta such that your left-hand side, which is this neural network on SI, to match the target, and that's your theta that you got in this step. And again, you have to do it's a value iteration. You have to iterate, because if you get theta this way, you have to iterate to recompute your right-hand side and then update the left-hand side. Right? You recall that when you do the Bellman, the value iteration, you compute the right-hand side and you update the left-hand side. You do this iteratively. So eventually you also have to have an iteration, which is you say let's see. So you iterate between these two steps. So you say you have a loop. But I think there's a little bit, did I specify everything? Yes, I think I specify, okay. So this is the loop. Maybe sorry, let's, okay, yes, so, I'm a little bit, I should save some space before. So let's say this is A, and I have a loop here. Right? So, but this is still not enough, because this loop is doing what? This loop is only doing the value iteration for this S1 up to Sn. Right? I haven't told you even how do you get S1 up to Sn, right? It's just a bunch of states that you have seen. So, and also even you can update, you can do this for every S, but a value iteration is not enough because our model-based algorithm has something even on the outer layer of the value iteration, right? So you estimate the model and you do value iteration, and then you estimate the model again, you do value iteration. Right? You have to do another outer loop to update your samples, right? So because when you do the model-based algorithm, you already have a loop outside the value iteration. So this is the loop for value iteration, and then we have another loop outside it, which is supposed to do the to iteratively update the model. So basically, you have another loop, and in this loop, you collect some data. Say S1 up to Sn. You collect this data from current policy. Right? You collect the data and then you do the value iteration on this data, and then you collect it again and you do value iteration. So this is how it imitates the model-based R algorithm for tabular case. Right? Because for the tabular case, we also have this outer loop where you collect data and you do value iteration, and you collect data, you do value iteration. So, okay, sorry, I think I'm missing even more step. You collect data, and also you need to also, in this outer loop, you also have to estimate the dynamics. Collect data, my bad. So collect data maybe 1 and 2, you estimate the dynamics. And then 3, you do the value iteration. And the value iteration consists of another loop, which is this. Any questions? I see some confusing faces. So basically, I think I erased that. Actually, it was part of here, right? So this was the part that we deal with the tabular case, right? So we have the 2 steps. I think maybe I should rename them as 1, 2, and 3. And there was a 1 step that was erased, which is the first step, which is the collect data. Right. So before, when you do the tabular case, you repeat between the 3. You alternate between the 3 steps: collect data, estimate dynamics, value iteration. And now, for the continuous state space, number 1 is still the same. Number 2 was done by this part of the board, right, where we learn this, with the supervised learning. And number 3 is done by here, this part of the board, where we do this A and B step, the A and B to kind of like to do the value iteration. So number 3 is this part, where we do the value iteration. And eventually, we have to do a loop for this 1, 2, 3 on top of this 1, 2, 3. Okay, I guess that's all for today. And for this whole course, I guess we have covered supervised learning, unsupervised learning, and reinforcement learning. Yeah, and we try to kind of like cover a little more and more deep learning these days. But also like some of these maths are included mostly because I think these are kind of the foundations of machine learning. So I hope you had some fun with the course. Thanks.